So today's lesson, we are going to look at the derivative of a tangent function, and then we're going to look at some applications of using these trig functions in the real world. So to start with the tangent function, we're going to do with what we know, sine and cosine. So we know tan is sine divided by cosine. There's going to be a lot of trig identities in this derivation, so I hope you like trig identities. Now, instead of using the quotient rule, we'll use the product rule. It's a little simpler. So we'll replace cosine on the denominator with an exponent of -1. And then to figure out what this derivative is, what we do is use the product rule. So first, we'll find the derivative of sine x and multiply by this cos x to the -1. And then add sine x by itself and multiply the derivative of that cos x to the -1. So when we do that, the derivative of sine x, we know that already, that's cos x. And the derivative of cos x to the -1, we're going to use our power rule here, or our chain rule, and we take the -1, multiply it in front, and then subtract 1 from the exponent, and then multiply by the derivative inside the bracket. And we know the derivative of cos x is negative sine x. So these two negatives are going to cancel, so we end up with a positive. And then we get sine squared x. And of course this -2 means divided by cos squared x. Over here we have cos x divided by cos x, so we're left with 1. Now we can go back and say, well, sine over cos is tan. So we have 1 plus the tan squared of x. And then here's a wonderful identity you may or may not remember, but 1 plus the tan squared of x is the secant squared of x. So this tells us that the derivative of tan x is secant squared of x. Now, similar to yesterday, if we had wanted to find the derivative of the tan of some function of x, well, first we say it's the secant squared of that function, and then we multiply by the derivative of that function. So we'll do some example problems. No need to worry about that. So before we do some example problems with our derivative of tan function, I wanted to do a little investigation. This is going to be an investigation with a pendulum. Now, we're not in the classroom, so we can't actually do this, which is a shame. It is easy to set up, right? You can make any pendulum at home with string and some sort of weight at the end of this string and attach it and have it swing back and forth. Okay? And you can compare, say, its maximum speed, where it has its maximum speed, where its minimum speed is, right? And you'll notice that the function looks like perhaps a sine function. Well, I can show that for you. My grade 11 physics students may remember this. This is a great software. It's free. It's called Algodo. If you're interested, I have a whole bunch of video tutorials and things like that on Algodo, but what I didn't teach you in grade 11 is something really cool. It's just a simple pendulum, a stick and a weight at the end. But I can right click and say show plot. And then I can change the y-axis to position in x. And now when I run the simulation, I lift it up, let it go, and there we go. We can perfectly graph the situation. And that definitely looks like a sine function. Right? It's a periodic function, it's repeating. You can see the amplitude slightly decreasing because there's some frictional forces. This is a fairly accurate program. So we have a frictional forces up here with the axle. I also have air on, so there's air drag. But you can see that even as the amplitude is dropping, we're still keeping a pretty good period, meaning the time it takes to do one full swing. You can analyze where the speed's the fastest. So the speed's obviously fastest right here in the middle. And that would be here, where you have the greatest tangent. And as you can see, as I move my mouse on there, it'll actually show me the dy by dx value. And so you can move it up and down and see where that value is the greatest. And it's right in the middle. It also finds the integral for you, but we're not going to talk about that right now. Right? You can go up and see where the speed's is the lowest value, which would be at the peak where you would have horizontal tangents. Right? And that's where this would be at either end of the swing. And if you wanted to even do a lot more analysis, you can export it as a CSV file, throw it into Excel or Sheets, and do a whole bunch of fun analysis on it. But I'll just leave it there for now. You notice I put an equation here. This equation is T stands for period, L is the length of the pendulum, and G is, for Earth, 9.8 meters per second squared. This tells you the time it takes for it to swing back and forth. Notice it doesn't have mass, so the mass of the pendulum doesn't matter. The amplitude, like how far it swings, doesn't matter. Right? And you can also create this equation here. If you wanted to create an equation for that actual curve, right? This is the amplitude. Of course, the curve is, you can make it a sine function with a phase shift if you wanted to, but you can also just write it as a cosine function. Right? And that would be its position, the horizontal position. And then you can find the derivative of that to show you where those maximum and minimum speeds are, and so on. So the first example says find the derivative for this function y, which is sine x plus tan x all to the power of 4. Okay, well this is a chain rule problem. So what we're going to do is bring the 4 out in front. So that's our coefficient, times by the sine of x, plus the tan of x, reduce the exponent by 1, so we're left with 3, and then multiply by the derivative inside of that bracket. So sine of x is cos x, and tan of x is our secant squared of x. There we go. So one step, we're done. We did it. So our second problem wants us to find the derivative of this function, x times the tan of 2x minus 1. Well, that's one function times another, so we're going to use the product rule for this one. So dy by dx equals, let's start by taking the derivative of x, which is just 1, and then we multiply it by our second function there, tan of 2x minus 1. And then we're going to add that first function x times the derivative of this second function. So to do that, the derivative of tan is the secant squared. So we'll write secant squared of, just leave that bracket alone, so 2x minus 1. And then multiply that by the derivative of that function in the bracket there. So derivative of 2x minus 1 is just 2. So in this case, we get, simplifying just a little bit, the tan of 2x minus 1 plus 2x times the secant squared of 2x minus 1. So our last problem says determine an equation for the tangent to the following function at the point with the given x coordinate. So the function is just tan x. Right? But to find an equation of the tangent, we need a point. So we have an x coordinate, x equals pi over 4. We're going to want to find a y coordinate. But again, remembering special angles, the tan of pi over 4 is just 1. So there's our point. We have the point of pi over 4 and 1. Now we need the slope of the line, or the tangent, at that point. So to do that, we're going to need the derivative. So the derivative of f of x is our secant squared of x. Alright, And to figure out what the slope is at pi over 4, we're going to find the value of this derivative at pi over 4. So the value of this secant squared of pi over 4 is 2. All right. You can figure that out if you want to remember your special angles. Just remember secant is just 1 over cos x, and that is all squared. And so now you can use your pi over 4 angle in cos and figure out that it's 2. Or you could put it on your calculator, but make sure your calculator is in radians, or you will get something completely different. Okay, so now we'll use the slope equation, right, which is m equals y minus y naught over x minus x naught. So our slope is 2. Our y coordinate is 1, so y minus 1. And our x coordinate is pi over 4, so x minus pi over 4. And then we can just simplify this a little bit. So we have 2x multiplying both sides by x minus pi over 4 gives us 2x minus 2 times pi over 4 is pi over 2 equals y minus 1. So y is then 2x minus pi over 2 plus 1. Which, if you want, you can simplify that a little bit further. So you can have 2x minus a half times pi minus 2.